PS, the neutral conductor can be derated on a 3-phase plug when its load is less than the phase conductors under specific conditions outlined by the National Electrical Code. The NEC permits size in the neutral conductor smaller than the phase conductors if certain requirements are met to ensure safety and proper circuit operation. Firstly, it is crucial that the neutral conductor does not carry significant unbalanced loads. This means the current flowing through the neutral should not exceed the maximum unbalanced current permitted for the circuit. A large unbalanced load would necessitate a larger neutral conductor to safely carry the current. Secondly, the neutral conductor must be sized in accordance with NEC Table 310.15b16. This table dictates the minimum allowable size for neutral conductors based on the ampacity of the overcurrent protective device safeguarding the circuit. This table ensures the neutral conductor can handle the expected current without overheating or posing a fire hazard. In a scenario where a 3-phase load exists and the neutral carries less load than the phases, the neutral is not considered to be carrying an unbalanced load, thus opening the door to potential derating. However, it's paramount to precisely determine the applicable size for the neutral conductor using NEC Table 310.15b16. This table cross-references the ampacity of the overcurrent protection with appropriate conductor sizes. Upon pinpointing the minimum acceptable size for the neutral conductor from the table, one must select a conductor that matches or exceeds that size. It is absolutely vital to never utilize a neutral conductor smaller than the minimum size stipulated by the NEC, irrespective of how low the neutral load appears to be relative to the phases. Choosing an undersized neutral conductor creates a significant risk of overheating, insulation damage, and potentially electrical fires. The purpose of the NEC is to establish standardized safety practices. Table 310.15b16 specifically addresses conductor ampacity based on insulation type and installation conditions, so using the correct ampacity ensures proper operation and prevents hazardous situations. Consider a 3-phase 208/120 volt circuit protected by a 20 amp breaker. If the load is balanced, and each phase carries approximately 15 amps, the neutral current will be minimal. However, even with this balanced load, NEC Table 310.15b16 must be consulted to determine the minimum allowable conductor size for a 20 amp circuit. If the table indicates that a 12 American wire gauge copper conductor is suitable for 20 amps under specific installation conditions, then that would be the minimum size permissible for both the phase conductors and the neutral, even if the actual neutral current is substantially lower. Now, consider a more complex scenario involving harmonic currents. Harmonic currents are multiples of the fundamental frequency, typically 60 Hz, and can significantly increase the current in the neutral conductor, even in what appears to be a balanced 3-phase system. These harmonics are generated by nonlinear loads such as electronic devices, variable frequency drives, and some types of lighting. In systems with a high concentration of nonlinear loads, the neutral conductor can carry more current than the phase conductors. In such cases, derating the neutral would be extremely dangerous. Instead, the neutral conductor may need to be oversized to safely accommodate the harmonic currents. Before making any decisions about derating the neutral conductor, it is essential to carefully analyze the load characteristics and determine whether harmonic currents are present. This can be done using a power quality analyzer, which measures the harmonic content of the current. If harmonic currents are significant, the neutral conductor should be sized to handle at least 150% of the maximum phase current. Furthermore, it is important to consider the voltage drop in the circuit. Voltage drop occurs when the voltage at the load is lower than the voltage at the source due to the impedance of the conductors. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. When sizing conductors, including the neutral, the voltage drop must be taken into account. Smaller conductors have higher impedance and will result in greater voltage drop. Therefore, even if the neutral conductor can be derated based on ampacity considerations, it may still be necessary to use a larger conductor size to limit voltage drop. To accurately calculate voltage drop, you need to know the length of the circuit, the current flowing through the conductors, and the impedance of the conductors. Online voltage drop calculators can simplify this process. Another important factor to consider is the type of insulation used on the conductors. Different insulation types have different temperature ratings. The temperature rating of the insulation determines the maximum allowable operating temperature of the conductor. NEC Table 310.15b16 provides ampacity ratings for conductors with different insulation types at different ambient temperatures. When selecting a conductor size, it is essential to ensure that the conductor's ampacity is sufficient for the expected current and that the insulation's temperature rating is appropriate for the ambient temperature. For example, if a conductor is installed in a hot environment, such as near a furnace or in direct sunlight, it may be necessary to use a conductor with a high temperature rating. In addition to NEC Table 310.15b16, there are other factors that can affect the ampacity of conductors. These factors include the number of conductors in a raceway or cable, the ambient temperature, and the presence of other heat sources. The NEC provides adjustment factors that must be applied to the ampacity ratings in Table 310.15b16 to account for these factors. For example, if there are more than 3 current-carrying conductors in a raceway or cable, the ampacity of each conductor must be reduced to account for the increased heat generated by the conductors. Similarly, if the ambient temperature is higher than 30 degrees Celsius (86 degrees Fahrenheit), the ampacity of the conductors must be reduced. It is important to carefully consider all of these factors when selecting conductor sizes to ensure that the conductors are adequately sized for the application. It is also important to consult with a qualified electrical engineer or electrician to ensure that the electrical system is designed and installed in accordance with all applicable codes and standards. In summary, while derating the neutral conductor in a 3-phase system is permissible under the NEC, it requires careful consideration of various factors including balanced versus unbalanced loads, harmonic currents, voltage drop, conductor insulation type, ambient temperature, and the applicable adjustment factors outlined in the NEC. Blindly applying derating without thorough analysis can lead to unsafe conditions and potential equipment damage. Reliance on NEC Table 310.15b16 is crucial, but it should be used in conjunction with a comprehensive understanding of the system's load characteristics and environmental conditions. Now let's delve into some specific examples to further illustrate the application of these concepts. Consider a scenario where you have a 3-phase 480-volt system supplying power to a bank of fluorescent lights. Fluorescent lights are known to produce harmonic currents, specifically third harmonics, which are additive in the neutral conductor. If the lighting load is significant, the neutral conductor could carry more current than the phase conductors due to these harmonics. In this case, derating the neutral would be inappropriate. Instead, the neutral conductor should be sized to handle at least 150% of the maximum phase current as recommended by the NEC for systems with significant nonlinear loads. Alternatively, you could use a specially designed harmonic mitigating transformer to reduce the harmonic currents in the system. Another example involves a 3-phase motor circuit. Motors typically draw a balanced load, meaning the current in each phase conductor is approximately equal. However, even with a balanced load, the starting current of a motor can be several times higher than its running current. This high starting current can cause a significant voltage drop in the circuit. Therefore, when sizing the conductors for a motor circuit, it is important to consider the motor's starting current and the allowable voltage drop. The NEC provides specific guidelines for sizing motor circuit conductors based on the motor's nameplate current rating and the type of motor. In some cases, it may be necessary to use larger conductors than would be required based on the running current alone to limit voltage drop during starting. Now let's consider the impact of different conductor insulation types. Common insulation types include THHN, THHW, and XHHW. THHN and THHW are both thermoplastic high heat resistant nylon coated wires, but THHW is also water resistant. XHHW is a cross-linked polyethylene high heat resistant water resistant wire. Each of these insulation types has a different temperature rating. For example, THHN is typically rated for 90 degrees Celsius in dry locations and 75 degrees Celsius in wet locations, while XHHW is typically rated for 90 degrees Celsius in both wet and dry locations. The higher temperature rating of XHHW allows it to carry more current than THHN for a given conductor size, especially in high ambient temperature environments. Therefore, when selecting a conductor size, it is important to consider the insulation type and the ambient temperature to ensure that the conductor's ampacity is not exceeded. Finally, let's discuss the importance of proper grounding and bonding. Grounding and bonding are essential for electrical safety. Grounding provides a low impedance path for fault current to flow back to the source, allowing the overcurrent protective device to trip and de-energize the circuit. Bonding ensures that all metallic parts of the electrical system are electrically connected, preventing voltage differences that could create a shock hazard. The NEC provides detailed requirements for grounding and bonding, including the size of the grounding and bonding conductors, the methods of connecting them, and the types of equipment that must be grounded and bonded. It is important to follow these requirements carefully to ensure a safe and reliable electrical system. In conclusion, derating the neutral conductor in a three-phase system is a complex issue that requires careful consideration of various factors. While the NEC allows for derating under certain conditions, it is essential to thoroughly analyze the load characteristics, the presence of harmonic currents, voltage drop, conductor insulation type, ambient temperature, and the applicable adjustment factors outlined in the NEC. Always consult with a qualified electrical engineer or electrician to ensure that the electrical system is designed and installed in accordance with all applicable codes and standards. Remember to prioritize safety and compliance when working with electrical systems. A mistake can lead to dangerous consequences. Understanding and following the NEC guidelines is a must for electrical safety. The National Electrical Code is not just a set of rules, it is a compilation of best practices developed over many years to protect people and property from electrical hazards. Keep up to date on electrical codes for maximum efficiency and safety in electrical projects.